All right, optimization day 2. The objective of this video, just like yesterday, is to use derivatives to set up and solve optimization problems. The bulk of this video, we're going to be working on 2 final examples. You should recognize this overview in these 2 examples from yesterday. But before we start today's examples, I want to briefly review some geometry tips, starting with a bunch of formulas. Can you recognize the volume formula for each of these shapes? Great. So I don't know if that was easy or hard, or if you used Google or not, but being able to recognize these formulas, where they come from, is going to be an increasingly important part of this course. By the time we get to integrals, we're going to be talking a lot about volume. And so you don't have to have them all memorized right away, but you need to be self-reliant. If you don't know a formula, you should Google it right away and move forward. And the more you use them, you will actually start to remember a lot of these. In reality, we don't just care about the formulas, we care about recognizing them. So consider these 4 questions. Exactly. We've got a triangular prism and a cone. And for each shape that we encounter in the real world, depending on the question we ask, we could be talking about surface area or volume. The first step when you encounter geometrical shapes in real-world examples is to make sure that you know what shape and what you're asking for. And then you need to know what formula to use, and that's either you look it up or you remember it. What formula would you use to measure each of these 4 things? Great, so hopefully the volume ones were easy for you, and maybe you used your notes or used Google or something, and that's fine. I imagine the surface area ones might have been slightly more challenging. So let me talk about the surface area. For the surface area of the Toblerone box, cardboard is only on the outside, so it represents surface area. Oftentimes when we try and come up with a formula for surface area, the trick is to kind of separate it into more reasonable pieces. For example, to create this box, I would have 2 ends that are triangle shapes and 3 sides that are just rectangle shapes. And so to create a formula for this, I'm going to need to know the length of this rectangle, and I'm going to need to know its height, but the height of the rectangle, if you look in the box, is the same thing as the side of the equilateral triangle, so I'm going to call that S. And now we can write an equation for the area of the 3 rectangles. We can just then add those up. We get 3 times SL. And then we have to add that to 2 times the area of these triangles. Each of the triangles' area is root 3 over 4s squared. And so if we add 2 of those and 3 of these, we get this surface area formula, which looks like that. Okay, enough with the geometry aside. If you want to think about something fun, think about what geometric shape would allow you to calculate the volume of the Earth's atmosphere. But I'm going to move on to some calculus. If you remember from yesterday, these were the 5 steps. We're still going to be solving optimization problems, so we're going to be using these same 5 steps. You should have these accessible in your notes, and you should follow along as I do the examples. Example 3. An open-top box is to be made by cutting congruent squares of side length x out of a 20 by 25 inch sheet of tin and bending up the sides. How large should the squares be to make the box hold as much as possible? So I'm telling you this is an optimization problem. Can you explain why? Right. Just like before, we're trying to maximize something. What are we trying to maximize? Yeah, we're trying to maximize the amount that the box can hold, but there's a better word for that, which is volume. So we're trying to maximize the volume inside this box. If you look at the diagram for a second, let's figure out what they mean by this first sentence. So it looks like there's a piece of tin, looks like this, and the whole piece was originally a rectangle that was 25 by 20, and then we've cut little pieces out of the sides. And the idea is we'll fold this side up and it'll become the side of the box. and it's going to kind of tape against this, and you can imagine physically creating it that way. So by telling us the size of the tin, they're controlling the size of the box. But obviously there are many different boxes you could make. If I cut these X's to be a little bit bigger, like if I cut the square out here, the sides of the box would become taller, which on one hand sounds like it would make the box bigger, but then at the same time, the inside base of the box would get smaller. So there's some tension there. The question is, how much is too much? How big should that square be? We'll set up the problem like we did in yesterday's video. Start with what we're trying to find, what the goal is here, and see if you can articulate what we're given. Right, we're trying to find the size of the squares, which if you think about it, is really X. This amount X right here is what controls how big the squares are in the corner. At the same time, we're trying to maximize the volume of this box. And we're given these two diagrams to help us understand how the numbers are all related to each other. So how do I start setting up this problem? Exactly, we want to come up with a formula for the volume of this box. What is it? Well, this is a normal box shape, so base times height times length is going to be a pretty good starting point. And then remember, the next goal is to get this to be a formula with a single input variable. I haven't filled in the variable yet because I don't know what it's going to end up being. So what I want to do is I want to replace B and H and L with expressions that have all the same variable. And maybe that variable is one of these three. Maybe it's something else. Well, I think you'll see a little hint in this picture. I'm going to scoot it over so you can see. If you think of the constructed box, the height of the constructed box is X, and it's labeled here, but I would expect you, once we've done a couple of these examples, to be able to look at this and see that this X distance right here, after it folds up, that's where the height is. So height is the same thing as X, which is worth noting as one of our given information. And then look at the base. So the base length here, they've listed as 20 minus 2x. Where did that come from? Well, look at the shorter side here, which is 20. The inside line, this dotted line, represents what's actually going to stay on the bottom. Everything else outside is going to fold up and become part of the side. So this line right here is the length that actually becomes this edge right here. And the length of this dotted line is 20, which is the whole distance, minus x on this side minus another x on this side. That's where 20 minus 2x came from. Finally, the length, which is this distance along the side, is the same thing as the longer side minus 2x's worth. So it's going to be 25 minus 2x. If you don't see where these values came from, please stop right now, look at this shape, maybe even take out a piece of scratch paper and try to create it, and try folding it up to create this box, and see if you can understand where those formulas are from. If you see where these come from, the next step is to use them to create my volume function, which is really just a matter of plugging in the expressions using x for B and H and L, and we end up with an expression that only has one variable. And then I'm going to go ahead and simplify this expression so I get a simpler looking function. And I end up with a cubic function that looks like this. What's the next step in the process of doing an optimization problem? Yep, endpoints and critical points. Extreme value theorem says that if this function has a max or min extreme value, it has to happen either at one of the endpoints or at one of the critical points. That's why we check them both. Endpoints happen when something about the problem is kind of limiting the types of numbers I'm allowed to look at, particularly the types of inputs. The limit on x in this case is that it has to be a positive number, right? We can't cut out a negative amount of the tin. So 0 is an endpoint. X equals 0 is the lower endpoint. And when we plug in 0, we get a volume of 0. What about the higher endpoint? Think about cutting x out of this box. What's the biggest cut I could make? Well, if you think about it, we're actually limited by the size of the material. If I cut out a square that's 10 inches, I would actually be cutting all the way halfway across this side, and I would be cutting halfway across from the other side as well, so that's the most that I could cut, 10 inches. That would be the maximum X value that I would consider making. And when you plug 10 in, you actually also get a volume of 0. Now, we don't expect these 0 volumes to actually be our maximum, but they're important to consider because they're going to help you interpret the next step, which is the critical points. How do you find critical points? That's right, set the derivative equal to 0. Favorite question of everybody right now. To do that, I got the derivative function. It turns out to be just a simple quadratic. And then I tried factoring out a GCF. But even factoring out a GCF, it turns out this is not a factorable quadratic. It doesn't mean it doesn't have solutions. We just can't find them by factoring. From Algebra 2, you hopefully remember that when you can't factor, you're going to have to use either quadratic formula, or in this case, we could actually use technology because we are calculus students and that's available to us. On the test, if you really came up against this and couldn't use a calculator, I would expect you to do quadratic formula. But let's save time and just do this using technology for now. So to solve this equation, I put the derivative into y1, and you could have used the factored form if you want. I used the non-factored form. It doesn't really matter. You will next graph it and find a good viewing window. I came up with something like this. And then we're going to look for the zeros. Now notice that there are actually 2 of them, so I'm going to find both of them. I do that by doing second calc, 0. And then I have to scroll all the way over to the left of the first point. Left bound, right bound, enter. And I get the first 0 is at 3.681. And then we repeat the process for the second 0, which turns out to be 11.318. And that gives me my 2 critical values. Next step is to plug in the critical values back to the function to figure out what the actual volume would be. And at the same time, we also need to prove, remember, that these values are actually, the value that we found actually does maximize volume. We need to prove that it's a maximum. Before I move forward, you should notice something about the second critical value. Exactly. 11 is outside of the bounds that we talked about at the beginning. We said whatever amount we cut out of this shape, it has to be more than 0 and less than 10. Well, 11's more than 10. So even though mathematically we came up with this critical point, given the situation and our understanding of it, we're actually going to ignore that number. And we're only going to pay attention to 3.681. When I evaluated my original function v, which was this function up here, and plugged in, I got 820.528, and the units would be inches cubed. So this volume, clearly bigger than 0, seems like a good candidate for the biggest volume that the box can have. But to mathematically prove that we've truly maximized volume, we need to use either the first or the second derivative test. As you guys know, I'm partial to the second derivative test, so I'm going to go ahead and find the second derivative by taking the derivative of the first derivative. And then I'm going to plug in my critical value. And when I simplify, I end up with a negative number, close to negative 91. So since the second derivative is negative at x equals 3.681, that means my original function must be concave down at that point, which proves that this value is truly a maximum. All we need to do now is write our final answer, which means you need to go back and consult with what format the answer is supposed to be in. Do we want to know the volume? Do we want to know the length? It turns out what we wanted was the size of the squares. We really just wanted to know how big x should be. Put it into a sentence. The square should have sides that are 3.681 inches long. And you're done. Let's take a look at one final example.